Hello. Hello. This is the second part of Chapter 6. We left off with this laws of thermodynamics. And if I click on here, again, this will be the second part of Chapter 6. And this is the one that is way more, I think, relevant to your lab, Chapter 6 lab on sun angle reasons. And also it'll be more relevant to you on your Chapter 6 quiz. The laws of thermodynamics are basically kind of the rules of how energy moves and how these general laws, there's a first, second, and third law of thermodynamics. And for the sake of time, so for example, I can just tell you, I'm much more interested really in the second law of thermodynamics that basically talks about that heat really has to move from hotter to colder bodies. So basically, and that's what we talked about. So when we study like physical geography, we live in the world of the second law of thermodynamics because we're really interested in energy transfers from areas of the Earth that have more energy, like the equator, to areas of lower energy, like the poles. And it's these movements of energy that really shape so much of the geography and uneven distribution of plants and animals and weather that we find so fascinating on the Earth. The video that I put here in Chapter 6 at the very bottom on the laws of thermodynamics will really nicely go over the first, second, and third law, and I would strongly advise you to do that. For the sake of trying to keep my lecture and focusing on the topics that I really want to lock in on, is I want to get on to radiation and the seasons. And there'll be simply just so many more topics and questions. But when we look at radiation, we really talk about radiation moving in a spectrum. And we move from the highest energy state of gamma radiation to the lower energy states called, there's certain energy that really the sun is responsible for. The sun emits a spectrum of all these different types of radiation. But the waves over here called gamma, X-rays, UV, and visible, this is really what we call the short wavelengths. And this is the energy the sun emits. The Earth is a little bit lower, it's obviously a lower energy state, and it tends to produce more of the infrared and the microwaves over in here in radio waves, and we call these long wavelengths. And we ultimately see it's the balance of the sun's shortwave radiation coming into the atmosphere and the Earth emitting out long-wave radiation back to the atmosphere that effectively regulates the Earth's climate. The key thing for us to understand is that the sun does not send all places to the Earth the same amount of radiation. Some places get more than others, and that's really the whole focus of our talk here. They get into here to describing some of the different wavelengths of radiation and their names and what they're responsible for and their energy states. The lower the number, the smaller the wavelength, the shorter the wavelength, the stronger the radiation. So most of these types of radiation you cannot even see. The only one that humans can visibly see is called visible light. And here is the visible light spectrum from red to your ultraviolets over in here. And this is what humans see. So you can see we see a very small portion of it. When we look at the sun's emission, we could actually see that the sun is primarily emitting a radiation wavelength about 0.7 micrometer. And if you were to come back to the chart, 0.7 micrometer actually puts you right in here in the visible light spectrum. So this tells us that the sun's primary emissions is actually visible light. This is why when we look at the sun, we actually see we almost get blinded because the sun is primarily emitting light. So when you get a suntan, it's primarily sunlight, visible light, that's causing your skin to change its pigment. And that's why, by the way, you might even argue some people around the world have different skin colors. It's because people near the equator get more direct sunlight, stronger sunlight, and that's why they tend to have darker skin color. Whereas you move towards the poles, you get less, and obviously the skin pigment changes. Now when we look at the Earth, you can see that the Earth is primarily emitting its radiation out at about 10 micrometer. And if you go back to this chart, 10 micrometer kind of puts you in the infrared wavelength range outside. So here's 0.7. 10 micrometer puts you in the infrared, and that's heat. which might shock you that the Earth is an emitter of heat. And where does the Earth get its energy to produce heat? Well, the Earth absorbs the sun's light, absorbs that light and converts it into heat, and it's this heat moving back to the atmosphere that drives our planet's weather and climate around the Earth. So they talk about here, there is a graphic called the inverse square law, and you could click on there and get a definition of it. The picture of it is broken, but if you were to actually put this into a Google search engine, you would find a nice graphic basically showing you that if you're a planet and you're farther away from the sun, the larger your orbit is away from the sun, the more the radiation from the sun spreads out over a greater area. And so that's why planets like Mercury, Venus, and Earth, being closer to the sun, they simply get more radiation than planets further out like Saturn and Jupiter and Neptune. So they have these formulas here telling you about how much energy, but this is really what shows you what the effect here is. As your distance from the object increases, the amount of radiation you get decreases, and this is called the inverse, and you could call this a negative correlation. The farther your planet moves away from the sun, the less radiation you're going to get from it. And so that leads us to say, well then, what causes the seasons over the Earth? And that leads us to our next topic, which is the nature of solar source of Earth's energy. Now, you would think what causes the seasons on the Earth is obviously our ultimate electromagnetic energy from our sun. And you would think, well, maybe the Earth gets closer or farther away, and that's what causes the seasons. And so maybe summer, it's actually warmer in summer because maybe the Earth just gets a little closer to the sun in summer and maybe gets a little farther away in winter. And using the inverse square law, you would say, well, then that must be what causes the seasons. Well, when I go to the next slide here, I'm going to show you that when we apply this idea, it's kind of complicated. Earth-Sun Geometry, Section G. And I'm going to kind of scroll down here. This is a fascinating graphic to show you that Earth's distance from the sun gets trumped by another factor here. This is the Earth's orbit around the sun, and this is the movement of a year. And the Earth moves around the sun counterclockwise, and on January 3rd, we actually get 5 million kilometers or 3 million miles closer to the sun than we do at our farthest point of our orbit. And after using the inverse square law, you should say, geez, Professor, it looks like this is all wrong. Because we know in January, when we're at our coldest, this is actually when the Earth is closest to the sun. So you would think, well, my goodness, we should be warmer. We should be warmer in January, and we should have our coldest month in July when we're 5 million kilometers or 3 million miles further away from the sun. It doesn't seem like the inverse square law is applying. Well, it actually has everything to do with the very first graphic. There's something that's trumping the inverse square law, and that is the fact that the Earth does sit at a tilt. And this 23.5 degree tilt causes at certain times of the year some parts of the Earth to get more different types of sunlight than other times of the year. So this tilt of 23.5 degrees actually influences two major factors that influence the seasons, and why people in North America and people in Brazil, people in Africa, people all around the world see and experience, and the animals and the plants for that matter, they have such a different view of the geography of the seasons, because winter and summer and fall and spring in Chicago, Illinois would feel very differently than maybe Rio de Janeiro, Brazil. So when we get into this, we have to figure out that this tilt is doing something that's overriding or trumping what we will discuss with the inverse square law, something is actually overriding the distance. The tilt of the Earth is doing two things. It's influencing the angle of the sun's rays striking down on the Earth, we will see, and influences the length of day. These two factors will be the key themes of you understanding the geography of the seasons over the Earth. And also, they will influence the length of day. And as we know, the length of day in summertime in the Midwest, we get 14 to 16 hours of sunlight, and in wintertime we only get about 7. We will actually find out at the North and South Pole there are times of the year where they get 24 hours of daylight and 24 hours of nighttime, and that is all influenced and controlled by the Earth's tilt of 23.5 degrees. So we will come back to that. I realize now that I'm just getting to the meat of really talking about topics that are going to be key for your sun angle lab. So I'm going to stop this, and we'll actually have 3 videos for chapter 6, and I'm going to break this one down right here because I think this is a good place to stop.